I'm going to start this lesson with a discussion of what a bounded set is. I could start with a set S in R. What that means is the set contains real numbers. So this is a particular kind of set, a real number set. A set in R is bounded. That's the term we're defining. If there exists an M in R, meaning there exists a real number, such that, now I'm going to start using this symbol, and I want you to kind of try to get used to this because it's going to be good shorthand, such that the absolute value of x is less than or equal to this M for all x in S. So this is very typical math type speak for what's going on, meaning that we have a set that's bounded if I can find some number so that my numbers in S are less than or equal to that number. And so this is kind of just sort of a set definition of this. Now let me show you a visual definition of what the function would look like. If I have a function like this, and I say that here is some M value, then if the absolute value of x is less than that M, I can kind of think about it as a sine wave maybe. I definitely have an M, and here would be negative M. But the absolute value of x, or absolute value of these values, would be less. Now, this is sort of a function version because I have x's and y's. A bounded function, which is a separate definition, is a real valued function whose image is bounded. Remember, image is like range. And so on the left here, I can clearly see that my f of x values are bounded. They're bounded by m and bounded by negative m. And that m could actually get a little tighter. I could come in a little bit closer and get a better m. So maybe that this is my m right here. And I can get extremely, extremely close. And if it was a pure sine graph or a pure cosine graph, then m would be 1. But all that's necessary for bounded is that there exists some m in R, and this would be for a bounded function, such that the absolute value of f of x is less than or equal to m for any x in the domain. So that's kind of an example, and actually the one I just drew was a cosine graph. Well, I guess sine or cosine depending on how it's shifted. In unbounded, and so unbounded means that I could just say a set is unbounded if there exists no such m. No such value exists. So that's kind of like divergent, or divergent series, but not quite. Unbounded just means I can't find any such value. So, most graphs that we kind of think of, curved lines or parabolas or anything, are actually unbounded or represent unbounded functions. So that's one definition. Now, some other ones that come into play that are related to this are, let's take a function that goes from one real number to another real number. So most functions actually do this. And then we're going to have a set A, which is going to be a set of real numbers. And f is increasing on A if f of x is less than f of x prime whenever x is less than x prime for any x or x prime in A. This means that the y values are less than each other whenever the x values are less than each other. And that's the basic definition of increasing. We can have some other ones, and I'm just going to throw the words down. Non-decreasing is a word that's used. Non-decreasing means less than or equal to. You can have constant, where you would take the same definition and replace the less than with an equal sign. You could have decreasing, which would then replace that with the greater than, and you can have non-increasing, which would be a greater than or equal to. So those are all kind of definitions that I would play, and I just wanted to do those in a quick way. It's not terribly complicated. Okay, another definition. Given f from a to b and y in b, and I hope you're sort of getting used to this notation that f is a function that goes from set A to set B, and y is an element of B. The inverse image of y under f, and this is written with an interesting notation, the inverse image of y in f is the set all x in A. Oops, I'm not right now. Such that f of x is equal to y. So this is similar to kind of the concept of the inverse function. It's just done from a set notation. So I have this blobby set A and this blobby set B, and this subset of B represents all the y's that actually could be traced back to an original element in A. And it's important to note that the inverse image is a subset of A. Not a function from B to A. This is what distinguishes it from being an inverse function. An inverse image is just a set or a collection of elements. It could be a small piece, it could be the entire piece, depending on how the function is. But the inverse image is actually the set. So this is all the little proofs about sets can apply to this. Sometimes we can look for a type of set that's very specific. So here's one for, if I take h defined as a function from R2 to R. Now, what I mean by that is R2 is actually made up of ordered pairs x, y, and R then would be made up of just z values. So I'm taking a function that goes from an ordered pair to 1. The level set of h with a particular value c is the inverse image of h on c, where c is an element of the real numbers. Now what that means is the level set is all ordered pairs, and this is the level set of this particular one, but all ordered pairs that yield a particular constant value c. So this isn't terribly complex to do if I have a very simple level set or simple function. So here's an example of this. This will kind of clarify what I mean. Let's say a of xy is just the sum of x plus y. So that's a very simplistic function from R2 to R1. What that means is that I'm basically looking for a c value that's the sum of that. And so one example of a level set would be to say the level set of c equals 1 is all the xy ordered pairs such that x plus y is equal to 1. Basically all the numbers that add up to 1. Well, that's not too hard to figure out. What are all the ordered pairs that add up to 1? That could be the line y equals negative x plus 1. And so that's a way to describe that. That would be a solution to that. The level set of c equals 1 is y equals negative x plus 1. All those points. And I could kind of continue with that. I could say the level set of sorry, C equals 2 is all the xy ordered pairs such that x plus y is equal to 2. For all possible C values, the level set would be what? Well, we can kind of visualize this if I graph the first two on a grid, and let me kind of turn this version on. If I graph the first line, the level set when C is equal to 1, when C is equal to 1, I have negative x plus 1. So I'm just going to quickly graph that line, and you guys can too. There we go. Kind of make sure I have a perfect diagonal in there. And then if I graph the other one when C is equal to 2, I just get negative x plus 2. And so that's a parallel line, just kind of right here. And you can sort of see if I sketch that this is going to happen through every C value throughout infinity. I'm just going to get the entire R2 grid. So for all C values, the level set would be, we could describe that as R2. Which, remember, that's kind of a cool way of saying all xy such that, actually I'm not sure what you would say. I think you just say all the xy ordered pairs. So R2 is the two-dimensional way of saying all real numbers. Here's another example. Let's say the m of xy is equal to x times y. And so for C equals 1, we have x, y is equal to 1. So if I sort of look at how that's going to look, I can graph y is equal to 1 over x, and y equals 1 over x looks like, let's see, 1 over 1. You guys should remember it looks like this. This is not a great sketch, but it works. Oops, I should do negative 1 right here. Then we curve around. I could actually do C equals negative 1. I should use a different color for this. And so xy equals negative 1, or y is equal to negative 1 over x, and that's the same thing, just in the other two quadrants. And clearly I can make any C value be positive or negative. Let's say I get C equals 2, and xy is equal to 2, or y is equal to 2 over x. Then I have the point 1, 2, and 2, 1. And so my graph's going to look something like this. And if I do C equals negative 2 and C equals positive 2, then I'm going to kind of get all of those. And you can sort of see how this is going to look. It's just kind of drawing further out a bit. And if I keep doing that through the history or through the end of time, then I'm going to have something that either gets further away and starts looking like this, or something that's going to get very, very close. And you should start to see what's impossible. I mean, what part, what's not going to be drawn. If I have the level set for all C, then I could describe that as all the xy ordered pairs in R2 such that x is what would have to be true here. You can probably kind of look at which ones are not going to be included. Basically the axes. So it says that x is not equal to 0 or y is not equal to 0. Or both. But that's included in that. So that's one way to kind of describe this for all C values. Okay, last example. This is going to be a doozy to write up, so I'm actually going to flip and type this because I can. This is going to be faster on me, and you guys can write this one, so here we go. Given two real numbers whose sum is between negative 8 and 8, and whose product is between negative 20 and 20, find the largest that one number could be. So this is done from a set standpoint. What I'm saying is that the sum is between -8 and 8. So I'm going to do this algebra style and say let x equal one number and let y equal the other number. And I know that if its sum is between -8 and 8, then x plus y's absolute value is less than or equal to 8. And the product is between -20 and 20, so xy is less than or equal to 20. Oops. So if x plus y is equal to 8, or is less than or equal to 8, this means that x plus y could equal 8 is one of the border points, and x plus y equaling -8 is the other border point. If I take both of these and graph them, get y equals -x plus 8 and y equals -x minus 8. And let's start to build a graph of what this is going to look like. These are two of my possible border points. So 1, 2, 3, 4, 5, 6, 7, 8. It's a little taller than I wanted it to be, or a little bit. Oh, I guess I can do this. That's better. So let's put a point down at 8 and put a point down at -8. I'm going to pause this so you don't have to watch me do it. Okay, I think I got those down. Now let's do the others. I want to do, this could mean x times y is 20 or x times y is -20. Those would be my two border lines. So I get y is equal to 20 over x and y is equal to -20 over x. Well, those are going to be kind of a pain to graph my points at 1. So let's try to put some points down that I can do. I could do 2, 10 and 10, 2 for the top one, and then if I did -2, -10, and -10, -2, and that would be for x and 20 over x. Then I could also do the opposites of those and have points for the other curve. So basically this is going to be all of those, and then I also can do 4, 5, and all those points, 5, 4, -4, 5, -5, and continue down. So if I plot all these, I'm going to have 2, 10, which I can do, and 10, 2, which is here, then 4, 5, and 5, 4. So let's pause and put those in all four quadrants. Okay, got those down, and then let's connect those. So that's going to be and then you can see we have areas of intersection here, 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 and here. So if I sort of thought about the region is going to have to be this region, this shaded region in here. Then my border points are occurring at plus or minus 2, plus or minus 10, or plus or minus 2, minus plus 10. These are where the four ordered pairs are. On all of them. So clearly my largest value, the largest that one number could be, so I got 2, 10. I also have, oops, hang on. Let's see, I'm not quite doing that right. Let's just list the points. 2, -10. Let's see. 10, -2, -10, 2, and -2, positive 10. So the largest that one number could be is occurring right there. The largest is 10. And I can now see that visually. So that's it. And there's only 3 problems this time. Or 4 problems, sorry. 122, 42, 43, and 49. See ya.